So we solve for r, the oscillation of the negative charge, and we could immediately get the dipole moment and how it oscillates. Little p is just minus q times r. But we need to think about something else. We need to realize that this E field, E naught e to the minus j omega t, creates many dipole moments. It doesn't just create a dipole moment of one atom in the material or the front surface, it creates dipole moments in all the atoms in the material. So we say it polarizes the medium. So let's look at what that means. So let me draw the medium's little atoms again. In the presence of this E field, E naught, say it's at its maximum value pointing up. I've drawn all of them a little bit warped because they've all been polarized, every atom. So let's see, there'll be a little bit plus on the top and a little bit minus on the bottom. And if I do this too fast, my pluses and my minuses will look the same. So they all do this. Therefore, they all get a little dipole moment. So we could give them all their own little p. All of them. So little p's will look like that. All the same. But what we want to do is define a bulk quantity. So we're going to define the polarization. Big P. Okay? This is a big P because the bump is above the equal sign. Big P equals minus n E R. Okay, here we go again with our negative signs. So big P is the polarization of the medium. N is the number of dipoles per unit volume. So it's basically the number of P's, but not in terms of their unit, but in terms of just counting them. How many dipoles per unit volume do you have? It's basically related to how many atoms do you have per unit volume. E is the electronic charge, and it is not negative. That does not mean plug in negative 1.6 times 10 to the minus 19 coulombs. It means plug in positive 1.6 times 10 to the minus 19 coulombs. A lot of confusion about negative signs comes from calling that negative, but E just means the charge of an electron or the charge of a proton. And remember, R is the position of the negative charge, and for little q, we wanted the dipole moment to point from negative to positive, so the minus sign, little p, was equal to minus qr. Well, that's why big P, it's equal to minus NER, because big P also points from negative to positive. So if E naught is pointing up, little p of each atom points up, and big P, the polarization, points up. This is the polarization of the material. This is something you talk about when you're thinking about electrostatics inside a material. This is not the polarization of light. Okay, we'll get to that later. This is a microscopic version of what's happening in a material. Okay? So, given all that, so you would think that we now very easily have big P, right? Big P is minus NER, minus N, charge of the electron. And then R, we just solved for. It was the charge of the electron, E naught, because that gave us the force in the top. And then in the bottom was all the terms, m omega squared plus j m gamma omega, and then minus k, I believe it was, and I will check. Yes, minus k. Oh, and then I was forgetting something, e to the minus j omega t. So that would then be how the polarization changes with frequency and how it depends on all those factors. Except that's not right, because each little atom doesn't just feel E naught. It feels E naught, the applied field, plus the field to all the other little polarized atoms, right? So they all make a field. So you have the case where you're trying to calculate P, and it doesn't just depend on E naught, it also depends on P, right? So this part isn't right. We've got to replace E naught with some combination of E naught and P. And that doesn't sound too hard, but this is where electrostatics inside of a material gets very confusing. So we'll go ahead and write that part out. But the atoms don't just feel E naught, they also feel the other polarized atoms. Is that right? Fields. So we got to figure out what to put here. And that's what's hard in electrostatics. So let me show you how you think about it. Let's see. So let's imagine you have, let's make it look the same. You have a material like this, and you've applied an electric field E naught to it. Therefore, you do get some polarization P. Okay? We're just trying to figure out how much polarization do you get, because we've discovered it's not simply adding up all the dipole moments. So the way you think about it is you have to go from this bulk description to a microscopic description. You have to think, what happens to this one individual little atom? So what you do is you imagine an empty little sphere inside the material. This empty sphere is where that atom would have been. Okay? And you ask yourself, what is the field inside that empty little sphere? Well, the E, this is called sort of the local E. The E inside that empty sphere, it's going to be E naught. It's going to feel that. We're making a superposition here. Plus the E field due to all that's created by all these polarization effects. Right? So what is that? Well, let's think a little bit more. How can polarization, how can it make a charge? How can it really do something like that? Because if you think about it, if we have a material and we polarize it, all that means is instead of the charge being in one place like this, it's just offset. So we have these little offsets where it's plus and it's minus, and it's plus and it's minus, and it's plus and it's minus. And if you zoom out, nothing's happened. All we've done is shift things. It's still neutral. Right? We haven't added any charge. It's still a neutral material. But what if you look at the top? Right? Then actually there's pluses up here in the top, even though they're balanced by those minuses. And if you look at the bottom, there's minuses down here at the bottom. So when you polarize a material, you can actually cause charges to appear at the surface. You're pushing some charge positive out here, you're leaving some negative there. And that's a real charge. That's a real charge. You can feel it creates electric fields. So even though it's a bulk material, things can happen at the surface. So then we ask ourselves, what would happen at this surface, this little hole? Well, normally, when you have the P, the E field pointing up, points up, and you get a P polarization field this way, it pushes, and you get the positive up top. Here, for a hole, it's the opposite. Right? For the little neutral atoms that were sitting on the edge, their positive have been pushed up, and you actually get negative surface charges here, and you get positive surface charges on that side. Okay? So the electric field you create in a hole is actually in the same direction. Each little atom actually feels a larger field due to the polarization of its nearby molecules. Okay? So you would have to actually add something, and the thing you would add is P over 3 times epsilon naught. Okay? And it's positive because of this effect. There's a little electric field that always points from positive to negative. P over 3 epsilon naught. Okay? So the field actually goes up at the local level. When you try to find this in a book, it's very poorly described, usually. Look for a section on the microscopic explanation. The macroscopic you don't worry about. Microscopic, it's here. And usually there's more terms. Usually you would also think about the real edges. Right? If you think about the edges, then it's positive over here, and it's negative here, and there's some electric force that field that way, and you have to add that in, and there's another term, more and more terms. Then actually usually think of a bigger hole, and you add up and integral all the elements in the hole. It's very confusing. But this is really all you need for what we're doing right now, if we're just thinking about light, because we don't care about edges. We're thinking about light inside of a giant dielectric material. And I forgot to say, this, where does this come from? This isn't magic. This is when you do the integral for some positive charge on one half of a sphere and some negative charge on the other half distributed in the way that would really happen, and you integrate to get the field. This is what you get. The electric field is P over 3 epsilon naught. Okay? So now we know the local field, and this, E plus P over 3 epsilon naught, is what we need to put here. E naught plus P over 3 epsilon naught. So that's what we're going to put there.